Hello everybody. For this week I'm going to upload a few recordings to explain a few things in a bit more detail and while writing down notes, which works a bit better on video than in a lecture, so it's easier to pass, things like that. So let's suppose that we observe a data set, a dependent variable or outcome variable y, and say that we have 4 observations. We have the observation 2, 3.5, 4, and 3.5. Now, the first thing we can do is we can calculate the average, right? Y bar, which is in this case 1 over 4 times the sum of these values. So 2 plus 3.5 plus 4 plus 3.5. In this case, that is 5.5 is 9.5 is 13 divided by 4 equals 3.25. 3.25. So let's add that to our data. Y bar 3.25, 3.25, 3.25, 3.25. Then the next thing we're interested in is knowing how much uncertainty is there in this data for every piece of information that we add. So we want to estimate the variance or the standard deviation, but actually we won't really talk about standard deviations anymore. We're mostly going to talk about variances because they're a bit easier to work with. You don't need to take this square root. To do that, in this case, we first calculate the deviance. Deviance equals y minus its mean. In this case, 2 minus 3.5 equals minus 1.25, and it's the same for all the other values. 0.25, 0.75, and 0.25. Now, there's an interesting thing with these deviances, and that is that their sum should always be 0. Otherwise, the mean would not be the average. Like the definition of the mean is that it's really between these deviances. Now, if we want to estimate the variance, right, which we call S square, in this case, what we can do is we can compute the sums of squares, which we call the total sums of squares, or earlier in the book the sum of squared errors, and that is because we can think of this as a model with only one parameter, mean, and this is deviation from the model. And we divide this by n minus 1, in this case 4 minus 1 equals 3. Now I'm going to make this a bit more general. I'm going to not say n minus 1 anymore. And I'm going to say that we're going to multiply this with the degrees of freedom in a model. In this case, the model is just the mean. We are not predicting y with anything but its mean. We could also think of it as regression with just an intercept and not a slope. The degrees of freedom in this case are n minus 1. Now, why is that the case? So the sums of square is the sum. Sums of squares is the sum for these deviances squared, right? So these values, we can square them, and then we can sum them. In this case, the result will be 2.25. Now, an interesting thing here is that we have to think about how many pieces of information do we actually have in this set of deviances, these D's. So here we have our data. And in our data, we have 4 pieces of information. 1, 2, 3, 4. 4 pieces of information in the outcome variable that we are interested in. Now, anything that we do here are just derivations, right, from the same data. It's just writing this data in different ways. That means that this doesn't actually add any information. We added 1 piece of information here, or not added, but we have 1 piece of information here. And because of that, let me actually draw it in purple. 1 piece of information here, which is, right, in this average. And because of that, we're only left with 3 pieces of information that are needed to calculate these deviances, and not 4. And that might sound weird, but I can show it. So let's say we want to calculate the deviances. And we now have to do minus 3.25. We compute the mean before we calculate deviances, and the deviances are based on the mean. And we compute the mean before we calculate variances, right? Or if you do a more complicated regression, we compute the parameters before we do any, we look at the variance around the parameters. So we need to know we are not estimating this mean at the same time as the variance. Okay, so we have minus 3.25. We also know that the sum of these deviances should be 0 by definition. Otherwise, the mean would not be the mean and the deviance would not be deviances. And let's see what we need to add. Let's say we add information. We have to add the 2 and the 3.5 and the 4. But do we still need to add the last value? Do we need to add that? So let's call this A. And now we can see that A is the only thing really that's left here that is unknown. And we have an equation, namely the equation that the deviances should sum to 1, 0. So let's try to solve this. 2 minus 3.5 equals minus 1.25. This one equals 0.25. This one equals 0.75. If we sum those, we get minus 0.25. So that means that we get an equation A minus, oh, let's do that in blue, minus 3.25 minus 0.25 equals 0. We can solve this to see that A equals 3.25 plus 0.25 equals 3.5. Now that is actually the data point that we had. So we did not need to know that data point. We only needed to know 3 things when calculating this variance, not 4. And this is what we mean with the degrees of freedom. This variance is based on 3 things that we don't know. The other thing, the last data point, is actually already predetermined by including the mean, which we calculated beforehand. And because of this, the degrees of freedom in this deviances, or this residual vector, or set of data points, is only 3, not 4. You can also think of it like this. If we have only one data point, let's say we have only the point 2 and nothing else, so y equals 2, then y bar equals 2, the mean equals 2, and we cannot have a standard deviation, we cannot estimate a variance. The variance will be 0 because this point is already at the mean. And that means that we lack an observation to have any sort of estimate for the standard deviation or the variance, right? It doesn't actually matter if you square or not, it's 0. Now let's say instead we have 2 data points, y equals 2 and 3.5. We can estimate a mean, 2.75, and we have deviations from that mean, right? 2.75 minus 2 and 2.75 minus 3.5, or 3.5 minus 2.75 actually. So that means that we get something that is not 0 for the estimate of the variance or the estimate of the standard deviation, which is nice. So by going from one data point to 2, we can start estimating a variance. But it's unfair to say that we added 2 data points. We only really added 1 data point, not 2. And because of that, when we look at this estimate, we should divide by, in this case, 1, not 2. So n minus 1. Okay, so let's clear this up a bit. Get rid of all these notes here that we have. There we go. So the sum of squares was 2.25. And I did not include that exactly here. You can try to verify it yourself, but that's 2.25. The degrees of freedom equals 3 of this particular model where we just have a mean. So that means that the variance estimate is 1 over degrees of freedom times the sum of squares, or 2.25 divided by 3 equals 0.75. We estimate this variance to be 0.75. That number tells us something about the uncertainty that our model, in this case only the mean, our model gives on the data. Now, we called this S square before. We're actually going to stop doing that. So that's a bit confusing. We're going to use a more general term, namely the mean squares. In this case, it would be the mean squares total, because we're basing it on this total sums of squares and the degrees of freedom from this null model with only a mean. So the mean squares. It's just a different name. It's actually the same thing. This is the total mean squares. It's just the variance that we already knew before. Okay, so now let's clean up some things again here. Let's clean up this mean. And just let's keep this. So now let's make it more interesting. And now let's form a regression model where we don't have just a mean, but also something else. So let's say I also observe an x. Let's keep things simple. Let's say the x is just 1, 2, 3, and 4, our predictor. So that means that we can draw a scatter plot. Zero, 1, 2, 3, 4 for the y-axis, and 0, 1, 2, 3, 4. That's 5 for the x-axis. Now which point do we have? We have for x1, we have the point at 2 here. For x equals 2, we have the point at 3.5 here. For x equals 3, we have the point at 4 here. And for x equals 4, we again have a point at 3.5 here. Now I can do ordinary least squares regression and estimate regression coefficients for a line. So this model would be y equals beta 0 hat, which means an estimated value, plus beta 1 hat plus times x, add subscripts here, plus error, which in this case will be observed from person I. Now if I estimate a model using least squares regression, in this case I would get the following parameters. The intercept would be 2 and the slope would be 0.5. So that means that if we add a line, it would start at this point 2 here, and then it would go up with half a point at each increase of x. So we can try to draw that. Oh, there we go. And we have this regression line. Okay, now let me actually write the parameters in here, which is a bit nice to read. Beta 0 hat equals 2. And let's do here. This part here, beta 1 hat equals 0.5. Now with this equation, we can compute the best prediction according to this model for y, which we call y hat. And y hat equals the same expression without the error term. So that is the height of the line. Right, so for every point, the height of this line. Okay, so let's take a look. For x is 1, it's 2 plus a half is 2.5. For x2, it's 2 plus 1 equals 3. For x3, it's 2 plus 1.5 equals 3.5. For x4, it's 2 plus 2 equals 4. After that we do that, we can now calculate these error terms, which is again, not x, of course, it's y minus y bar, y hat. In this case, it would be 2 minus 2.5 equals 0.5. For the second value, it would be 3.5 minus 3 is 0.5. For the third value, it would be 4 minus 3.5 is 0.5. And for the last value, it is 3.5 minus 4 is minus 0.5. We can see that here because here we have a deviation of minus 0.5, where here we have plus 0.5. Now again, this error set of errors is not without constraints. There are now actually two constraints, namely let me draw it in purple to get some other colors in there. The sum over all values of the error terms equals 0. This sum equals 0. Is that correct? Well, minus 0.5, minus 0.5 plus plus, so that indeed equals 0. But there's another constraint. We also assume that the error is not correlated with the predictor x. And because the error has a mean of 0, we can do some algebra, and I'm not going to do that here, so just trust me that it's correct. Say that the error times x, the sum of those values should also be 0. Let's take a look. We have, so that's this times that, that times that. So 1 times minus 0.5 plus 2 times 0.5 plus 3 times 0.5 plus 4 times minus 0.5. Okay, so basically we have minus 0.5 and plus 0.5 in this case, so that becomes a bit easier. We have here 1 plus 4, so that's 5, and we have here 2 plus 3, so that's 5. So we see 5 times minus 0.5 plus 5 times 0.5 indeed equals 0. So now we want to calculate the residual sums of squares of this model. And we're actually going to do the exact same thing that we did before. So what we're going to do is this, let's draw it here. The residual sums of squares equals the sum of these error terms, not the deviances, but the error terms squared. Right, and error term is y minus y hat. So we can do that, and in this case, that is 1. Right, this is squared, it's actually easier, minus 0.25. Sorry, 0.25, 0.25, 0.25, 0.25, so the sum of that equals 1. So now we again want to average this, and we want to calculate a mean, let's make it in red, mean squares of this residual. So the variance that's left of this implied by this model. Now to do that, we know we need to multiply this residual sums of squares, with this 1, with 1 over the degrees of freedom. So we need to know the degrees of freedom. Now in this case, the degrees of freedom equals n minus 2. And why is it 2? Because we have 2 pieces of information that we lost in estimating these 2 parameters. First we had only one, because we only had the mean, which in that case is the intercept. But now we had 2, because we also had this other parameter. That means that the degrees of freedom is now, in this case, 2, or n minus 2. And if you're really interested in this, you can practice at home. You can see that you still have 4 pieces of information in y. 2 of them are lost in the parameters. So that means that in this set of errors, we only need to add 2 pieces of information. So if we add this one and this one, then we can solve and we can calculate that the third value should be 0.5 and the fourth value should be minus 0.5. Now, that's a bit of an advanced thing. It's not required for the course, but if you're interested in this and interested in seeing why that's the case, then try to do that. Try to follow the math where you fill in these expressions and take these 2 equations into account. Okay, so now we know that the degrees of freedom in this case is n minus 2. And in general, for any regression model, degrees of freedom equals the number of observations minus the number of parameters. Right, so this one minus that one. For the residual, degrees of freedom of the residuals. You can call this res. Right, so we know that that should be 1 over 2 times 1 equals 0.5. So let's clean up a bit here and add all this information together. So we have the total sum of squares from the model where we only have a mean equals 2.25. We also knew that the degrees of freedom here were 3. There are 3 degrees of freedom that we used to calculate this variance. N minus 1 because we used one mean. Does that mean that the mean square equaled 0.75? Then we had for our regression model, so this one here, the residual sums of squares equals 1. The degrees of freedom equals 2. Leading to a mean sums of square of 0.5. Now what we're actually interested in is seeing how much of the variance is explained by the model. And we know that the total sum of squares equals the residual sums of squares plus the sums of squares explained by the model, which you could also see as the distances from the mean, which I didn't draw here, to this line. So let's do that in red. So because of this, we can say that the sum of square of the model equals the total sum of square minus the residual sums of squares. That in this case, that would mean 1.25. Now what we're actually interested in is calculating this mean square, right? Because this sum, we're summing over things, but that's also a bit different how much information is in there. We want to know how much information is really in this model sums of squares. Now degrees of freedom always need to add up. And 1 degree of freedom is always lost in the mean. Basically in this total model, this is actually a model with 1 parameter, namely the mean, so that already lost 1 degree of freedom. Now degrees of freedom need to add up. So that means that the degrees of freedom the total model, right, of the total sums of squares, should also be decomposed as the degrees of freedom of the residual and the degrees of freedom of the model. In this case, we only have one model. It gets a bit more complicated later on in the course where we have multiple models. So that means that the degrees of freedom here is 1, namely 3 minus 2. That's the degree of freedom we're left with. We had 3 degrees of freedom in this model with just a mean, right? We're left with 2 degrees of freedom in the variance of the model that also has a slope. So that means 1 degree of freedom got into that model, which is here. So the mean square is this divided by degrees of freedom, is in this case the same thing. Now let's add some subscripts still. Total, the green, total, residual, and model. Now why is this interesting, or why is this important? The reason is that we want to see if our model is explaining variance in the outcome variable. So what we want to see is if this estimated variance that is explained by the model, if that is high, or at least if it actually is anything but 0, if it's above 0. So we want to see if that thing is high, especially in comparison to this residual variance. And we need to take it into comparison. We don't know if, for example, variance of 1 is high or low. If we see that the mean variance, so the variance of the model, that the model explains is 1 point, but there's a residual variance of like 1,000 points, then okay, we know that's actually not explaining much, right? That's why we need to take these two things into account. Now these two values we use. And there is a test statistic that we can use called the F statistic. It has a distribution. The distribution has some shape like say 0 and then like it has some like curve like that usually. It can have quite some different curves. And F equals the model mean squares divided by the residual mean squares. If the model mean squares is 0, then this is just going to be 0. That's the minimum you can get. Variance cannot be negative. If it's the same as the residual, it's about comparable. It would be 1. Ideally, we want it to be even higher than that. Right? So we can see, okay, our model is explaining relative to the to what is unexplained variance, our model is explaining quite a lot. Now this thing has a distribution, so we can use it in significance testing. The interesting thing about it is that it has 2 degrees of freedom, namely this one, the model one, and this one, the residual one. So the way you would write this, say F with 1 and 2 degrees of freedom, and usually the second one will be much larger, right? Because sample size usually aren't 4, there will be like 100 or 200 or so, or 50 or 10, at least more than 4. So F 1 and 2 degrees of freedom, so 2 types of degrees of freedom, equals, and then this ratio. In this case we have 1.25 divided by 0.5, so that equals 2.5. Now the question is this a high value, a significantly high value, under a null model where we assume that the model is not explaining any variance. Okay, so let's take a look in JASP. So here we have the data, y and x. Let's actually look at the distributions panel here. F distribution. You don't have to do this. You can just, the output will give it, but just for the sake of looking at this. So we had degrees of freedom 1 and 2. And with an F value of 2.5. That gives me a p-value of 0.25, which in this case would not be significant. So let's also look, if you actually do the regression analysis, which is what you would do instead of this, because you don't usually compute this by hand. Let's do linear regression. The dependent variable y and the covariate x. Method here we leave on enter, and we get a lot of information here. We get a p-value of 0.25, in this case 0.255. Let's see here, it says 0.25. There's probably a rounding error there. So here we get all our information. We see here the regression sums of squares, 1.25. And this is a bit of a weird thing. They use regression, not model. I would use model because R is also for residual, but you see it sometimes in the output. So the model, sums of squares, 1.25, the residual, 1, and the total, sums of squares, of 2.25. You see here that the total, so the total is of the null model, there's 3 degrees of freedom, and those are decomposed as 2 and 1. Here, we actually don't see the mean square of the total, it's not that relevant. But these are relevant because these make up the F value. So 1.25 divided by 0.5 equals 2.5, and that is the p-value. So we see here, sums of squares divided by the degrees of freedom gives the mean squares. These things, the ratio gives the F value, that gives the p-value. And we can also see the coefficients. We see they're estimated to be 2 and 0.5 with associated p-values as well. Now note here that the p-value of this is exactly the same as the p-value of this regression coefficient. That's because we only have one regression coefficient. But if we would have multiple regression coefficients, then the F value would tell us something about how much variance is explained by the regression model in total, compared to a model with only an intercept, which in this case is only called H0. Right, so this is a model where we only have a mean, which is not that relevant. We don't really care about that. So the F value then would say, okay, how much do all the regression coefficients combined explain in the data? We can also here see the R squared and an adjusted R squared, which adjusts for the number of predictors.